This video will begin talking about truth functional argument forms. And here we're going to talk about truth tables, truth functional logical operators, and basic truth functional argument forms. This is a truth table. So as you recall from your reading, truth functional logic deals with the logical relations between propositions, and we use variables to represent propositions. And what we're really looking for are logical relations between propositions. Remember from earlier in the course, we said that every proposition is either true or false. And here we're going to call that the truth value of the proposition, basically whether it's true or false. That's its truth value. So every proposition has one of two truth values. And if we take two propositions here, A and B, that gives us four possible combinations of truth values, or we can say four possible scenarios with respect to how the truth value of each of these propositions might turn out. So in the scenario numbered 1 here, A and B are both true. And in the scenario number 2, A is true and B is false. In scenario number 3, A is false and B is true. And in scenario number 4, both A and B are false. So this is what the truth table represents here. It basically gives us a visual representation of the possible scenarios with respect to the truth values of these two propositions taken together. Okay, now we're going to add a statement. If A, then B. We call this a conditional, you recall from the reading, and we represent this with an arrow, right? Again, A in such a construction is the antecedent, and B is the consequent. It doesn't matter what letters we used. We could say if X, then Y, if W, then U, right? We could say if B, then A. And if we said if B, then A, then B would be the antecedent and A would be the consequent, right? So whether it's the antecedent or consequent depends on the proposition's position in this logical relation with the other proposition. What we're saying here is that if A is true, then B will also be true. And so with the truth table, we can give the truth value of if A, then B in each of these four scenarios. And it will be like this, right? In the scenario where A and B are both true, then the statement if A, then B will be true. But if A is true and B is false, then the statement if A, then B will be false. Because again, when we say if A, then B, we're saying that if A is true, then B will be true. But if it turns out to be that A is true but B is false, then it will be false that if A is true, then B is true. And so if A, then B will be false in that scenario. But if A is false, then if A, then B is going to be true. So that is how the truth values of if A, then B look on the truth table. That basically gives us the meaning of if A, then B in truth functional terms. Now, if we flip it around and say if B, then A, then we'll have something different. It'll be true if they're both true, and it'll be true if A is true but B is false. But it will be false when A is false and B is true, right? Because again, we're saying now that if B is true, then A will be true. So if B is true but A is false, as is the case in the third scenario there, then this statement will be false. But if they're both false, then it will be true. So take a look at that for a second, and you will understand what's going on here, I think. Okay, now we have another statement. A, if and only if B. This is basically the combination of if A, then B, and if B, then A. So if we give the truth values of this statement on the truth table, it'll be true if they're both true or if they're both false. But in any situation in which one is false and the other is true, then this statement will be false. Okay. Now, if we flip that one around, then we get the same truth values on the truth table, which means that it doesn't matter which order we say we put A and B in that construction, because it's a symmetrical relation, right? B if and only if A means the same as A if and only if B. That's not the case with the regular conditional, but with this, which we call the biconditional, that's the case. It's a symmetrical relationship. Okay, so you recall from your reading, I hope, the argument form called modus ponens, which is one of the conditional argument forms, which is one of the valid forms of a conditional argument. And we're going to use the truth table to illustrate its validity. So here's the argument form modus ponens on the right there. If A, then B, A, therefore B. So what we're going to do is eliminate the four, from the four possible scenarios, whatever the premises of this argument dictate, right? So the first premise is if A, then B, right? That will eliminate scenario 2, because scenario 2 is the scenario in which if A, then B is false. Again, why is that? Because that's the scenario in which A is true, but B is false. And if A, then B just means that if A is true, B will be true. So if the premise if A, then B is true, then scenario 2 is ruled out, right? So that's why we put that in red, the same color as the premise, so that you know that it's premise 1, which eliminates that scenario number 2 as a logical possibility, right? If the first premise here is true, then scenario number 2 cannot be the scenario that is the case. Okay? All right. Now, the next premise is A. And that means that if that premise is true, we will eliminate the scenario in which A is false. And those are 3 and 4. So since A is true, we know that scenario 3 and 4 are not the case, which leaves us with only one possible scenario, right? If our two premises are true, then scenario number 1 is the only possible scenario that can actually be a fact. And therefore, if we look at that scenario number 1, the only possible scenario there is, given our premises, we find that B is true in that case, right? And so that means that our argument's valid, because really what we found out here is that if the two premises are true, then the only possible scenario with regard to the truth values of A and B, that's the first one, is the one in which B is true. In other words, if the two premises are true, the only logical possibility is that B is also true. All right, now, this is an argument form called affirming the consequent. We call it affirming the consequent because we start out with the conditional, if A, then B, but our second premise affirms B, which is the consequent. And then the conclusion is that A is the case. Now, this is actually a fallacy. It's not a valid argument form. And using the truth table, we can see why that is. So again, right, the first premise says if A, then B, and that means that scenario 2, in which if A, then B is false, is not the case. Yeah, that eliminates number 2 as a possibility. B tells us, right, that B is true. And so that eliminates scenario number 4, which is the scenario left in which B is false. Now, in scenario number 1 and scenario number 3, B is true. And in scenario number 3, A is false. So what we found here is that given these two premises, right, if these two premises are true, that still leaves a logical possibility in which A is false. Therefore, we cannot conclude on the basis of these two premises that A is true, and the argument is invalid. Okay, here's another one, modus tollens. If A, then B, not B, therefore not A. We could also call this denying the consequent. Now, we're going to add some columns to our truth table, and we need to add these columns for the proposition not A and not B. Yeah. So if A means that the proposition A is true, then not A will basically be saying that the proposition A is false, right? And therefore, on the truth table, any place where A is true, not A will be false, and any place where A is false, not A will be true. Likewise, any place where B is true, not B will be false, and in any scenario in which B is false, not B will be true. We just do that for making it easy for ourselves. We don't need to do that to use the truth table, but we need to illustrate what the truth value will be for the negation of propositions on the truth table, right? And it'll be the opposite of that proposition, right? Obviously, if A is true, then not A is false. And if not A is true, then A is false, okay? And we want to do that so that we can easily sort of refer to the truth table for the truth value of not B, since that is the proposition here in the second premise. So again, our two propositions allow us to eliminate lines on the truth table, possible scenarios. The first premise allows us to eliminate scenario 2, because if A then B is false there. But our premise again says that if A then B is true. And then the second premise, which says not B, will eliminate any scenario in which not B is false. Or in other words, it will eliminate any scenario in which B is true. So there we have it, scenario 1 and scenario 3. So we can cross out those lines. We rule out those as logical possibilities on the basis of presuming that our premises are true. And that leaves us with only the last fourth possibility. And our conclusion says, therefore, not A. So we're going to look at that last possibility, and we find that, in fact, not A is true, right? Or in other words, A is false. So given the premises, the only logical possibility is that A is false. Or, in other words, not A is true. And therefore, our argument is valid. Our premises show us that the only logical possibility is what's given in the conclusion. Okay, so now we're going to compare modus tollens, which was a valid argument form, as we just shown, with denying the antecedent, which is a fallacy. So we have our modus tollens on the left side here. And on the right side, we have the truth table prepared for the form of denying the antecedent, right? And it goes if A then B, not A, right? Again, A is the antecedent, and we're denying it in the second premise. Therefore, not B. And we've seen that what we've done here in the second scenario, the second line here, is that the if A then B is false there, so that's going to be ruled out by our first premise. So we've highlighted that F there in red to make that clear. The second premise tells us that not A is true, and therefore we're going to rule out the first line of the truth table where not A is false. You can see that blue F there indicating that. And so our two premises allow us to rule out those two possibilities on the truth table. Now our conclusion tells us not B, but we have again two remaining scenarios that are logically possible given the premises. That is number 3 and number 4. But in number 3, not B is false, whereas our conclusion is that not B is true. So our premises have left us with the logical possibility that the conclusion of this argument is false, and therefore the argument is not valid.